All right, welcome, brothers on the floor. I am absolutely thrilled to walk you through this explainer today. We're going to dive right into our strict Standard Operating Procedure 21 for tackling an inlet pH sensor error. Look, if you're operating a wastewater treatment plant, you already know the sinking feeling when that SCADA screen starts flashing red with a pH alarm. You have got to act fast. So we're going to break down exactly how to handle this beast, protect our biological treatment, and keep the plant running completely smoothly. So here is our roadmap for today. 1. Intro and symptoms. 2. Root cause diagnosis. 3. Emergency fixes. 4. Cleaning and calibration. 5. Prevention. And finally, 6. Monitoring and summary. Let's jump straight into Section 1, Intro and symptoms. Okay, as a quick refresher, our inlet pH sensor is a 4 to 20 milliamp transmitter system. It basically uses a glass electrode and a silver-silver chloride reference electrode to measure hydrogen ions. But why does this actually matter to us on the floor? Well, because this sensor directly controls our acid and base dosing pumps. If this little sensor fails, our chemical dosing goes completely off logic. We end up wasting literally thousands of dollars in chemicals, we completely ruin our coagulation process, and worse, we risk sending a massive pH shock right into the biological bugs downstream. Now, I really need you to watch out for these exact symptoms on your shift. Picture this. You're looking at the SCADA values and they're jumping wildly. I mean, going from 6.0 up to 9.0 and then crashing back to 5.5 in just a few minutes, even though the inlet water hasn't changed at all. Or maybe your dosing pumps are running nonstop, or they've just completely frozen up. You might even see the transmitter itself flashing a bright red out-of-range fault. Or, sometimes you just notice the inlet water suddenly smells or looks totally off, but that pH value on the screen hasn't moved a single inch. Guys, these are your major red flags. Moving right along to Section 2, Root Cause Diagnosis. The second you see a red flag, your absolute first go-to action is to grab a well-calibrated handheld meter and take a fresh sample right there at the online sensor's location. Read them side by side. If the gap between your handheld and that SCADA screen is greater than 0.5, brothers, we have a confirmed sensor error, no question. Now, if the deviation is less than 0.2, it's probably just a normal fluctuation in the water source, so just keep an eye on it. Assuming it's an error, step 2 is getting hands-on with a physical check. Safely pull the probe out, but hey, make sure you lock out the automated controls first, right? Check the glass bulb itself. Is it totally coated in brown oil, maybe white calcium scale, or even green algae? Check the cables for rat bites or loose connections. Is the reference electrolyte completely dry? Then step 3 is your calibration check. Rinse the probe with distilled water, and here's a massive pro tip straight from the manual. Never, ever wipe the glass with a paper towel. It creates static electricity and ruins the reading. Just put it in a pH 7 buffer. We want to see a zero offset of 0 plus or minus 30 millivolts. For step 4, check the temperature. Compare the probe's temperature reading against a real thermometer. If it's off by more than 2 to 3 degrees Celsius, that built-in temperature sensor has definitely failed. So I really want you to burn this specific number into your memory. 59.16. When you go to check the calibration in your pH 4 or pH 10 buffers, remember that our ideal acid slope is 59.16 millivolts per pH unit, assuming we're at 25 degrees Celsius. We absolutely need to see that slope sitting healthy between 90 and 105%. If it drops outside that range, the sensor just isn't responding correctly to the hydrogen ions in the water anymore. Let's wrap up this diagnosis. Step 5. Grab a multimeter and measure that 4 to 20 milliamp loop, just to be totally sure the transmitter itself isn't the problem. Step 6 is all about the environment. Look around. Is the probe installed way too close to the chemical dosing point? The manual strictly states it needs to be at least 10 to 20 pipe diameters away just to ensure proper mixing. Are there air bubbles blocking the glass? And finally, step 7. Check your maintenance logs. Honestly, if that combo probe has been soaking in industrial wastewater for over 18 to 24 months, it might have simply aged out. Nothing lives forever. Which brings us to sections 3 and 4, emergency fixes, cleaning, and calibration. Listen up, guys, because this is literally our highest priority. The absolute most critical thing I need you to do in the first 2 hours of a failure is switch the dosing system to manual immediately. Never, ever leave it on auto if you even suspect the sensor is faulty. You are going to manually adjust that dosing based entirely on your handheld readings. Make sure you tag the SCADA screen so the control room knows what's up, and grab a lab sample for a true baseline. We have to prevent a chemical overdose that could completely crash our biological basin. Okay, once the system is safely running in manual, we move to the root cause fix. If the probe is dirty, you have to clean it based on the specific type of dirt. Use a mild detergent or Pepsin for hydrocarbon oils, and please do not use harsh solvents like acetone. They will literally eat the polymer and ruin the equipment. If you're dealing with calcium scale or biosludge, soak it in zero point 0.1 molar hydrochloric acid for about 5 to 10 minutes. After that, rinse it off and let it soak in 3 molar potassium chloride for at least an hour before you even try recalibrating. We are aiming for a slope greater than 95% and a zero offset of less than plus or minus 20 millivolts. But what if you put in all that work? You scrub it, soak it, and it still fails. Well, that brings us to the magic number 85. If you've cleaned the probe perfectly, soaked it properly, and that slope is still sitting under 85%, it's completely dead. Or if the ceramic diaphragm is totally clogged up, or the probe is over 18 months old, just throw it out. Seriously, don't waste your shift fighting a dead probe. Go straight to the warehouse and install a brand new electrode. All right, Section 5, Preventing Recurrence. Because let's be honest, prevention is way cheaper and a lot less stressful than a midnight emergency. If our inlet water is heavy with grease or sludge, we absolutely need to be utilizing auto cleaners like automatic jet sprays or ultrasonic cleaners. But even with those running, we must enforce strict weekly manual cleanings. For our most critical dosing points, installing a redundant backup sensor is an absolute lifesaver. And finally, always keep a spare combo probe, fresh calibration buffers, and 3 molar KCl in the warehouse. And check the dates. Don't let those buffers expire on the shelf. And finally, Section 6, Monitoring and Summary. So, the fix is in place. Now what? Well, for the next 7 to 14 days, you are going to use this exact table format to rigorously log the system's performance. You'll record the date and time, the online SCADA pH, the handheld pH, and then calculate that deviation. You'll also log the temperature and the calibration slope. I know it sounds tedious, but this daily discipline is exactly what proves whether our fix is actually holding up under real, gritty plant conditions. We only declare the incident fully closed and resolved when we hit these exact success criteria. We need to see less than a 0.2 deviation between the online sensor and the handheld for 7 straight days. The auto-dosing mode must remain perfectly stable, no wild jumps on the trend graph. The probe's T90 response time, which just means how fast it reacts to a pH change, has to be under 30 seconds, and we want absolutely 0 SCADA faults for 14 straight days. I really want to leave you with this final, incredibly powerful lesson from the SOP. The pH sensor is the gatekeeper of our entire treatment plant. Think about it. A tiny error at the inlet amplifies into a massive, disastrous violation at the outlet. Because of that, you can never completely trust the online value without periodic manual verification using your handheld meter. It's your plant brothers. So I have to ask you, when was the last time you manually verified your gatekeeper? Think about that on your very next shift. Thanks so much for joining me on this explainer, and stay safe out there.